So let's look back at nucleophiles and electrophiles and clarify a few things. So let's recall what we know. Nucleophiles love positive, right? And they are a lone pair donor, so they donate an electron pair. And electrophiles love negative, and they accept an electron pair. Something interesting, let's go to this Lewis base. A Lewis base can act either as a Bronsted base, which is a proton acceptor, right? Or a nucleophile. So a Lewis base is defined as a Bronsted base when it donates a pair of electrons to a proton, and that's the key. If it's donating to a proton, it is considered a Bronsted base. If it donates the pair of electrons to an atom other than hydrogen, it's considered a nucleophile. So let's look back at the chart we created, or rather the diagram we have. This yellow zone is nucleophile. This blue zone is your Bronsted-Lowry only. So this is where you're talking about the proton. So do you donate to your electrons to a proton? You're a Bronsted-Lowry base. Do you donate to anything other than a proton? Then you're considered a nucleophile. So let's go to the other side of things and see that a Lewis acid accepts a pair of electrons from a Lewis base, period. It can be a proton. So where we have this exclusionary situation on the left, we don't on the right. But for our sanity, we're going to say a Bronsted-Lowry acid is the Lewis acid if the H plus accepts the electron pair. So we're putting the same parameters up so that as we investigate, we're not having to overthink ourselves. And then we're going to say it's an electrophile when it accepts the electron pair and does not involve that proton. So similar breakdown of the diagram over here. I think that'll make it a little bit easier as we're naming, is this a Lewis acid base, or is it Bronsted-Lowry? Is it a nucleophile? Is it electrophile? I think that will make it a little bit easier. Okay, so we have two different situations. We have the blue strip and we have the yellow strip, and we're going to assess the base. So first, we have hydroxide, hydroxide. So we can agree those are bases. In the case up top in the blue, this hydroxide is going to donate its electrons to form the bond with the H+. These electrons that were between the carbon and the hydrogen are going to fold in to form the double bond there. And these electrons are going to go up top here. So we're going to wind up with this species and water in the end. This hydroxide donated to a proton. So it is a Lewis base, but then the question is, what kind of base? Is it a Bronsted-Lowry base or is it a nucleophile? Here, it's acting as a Bronsted-Lowry base because it is donating to the proton. That's the key. And if this is the Bronsted-Lowry base, this is the Bronsted-Lowry acid. Okay, so this top one is an example of it acting as a Bronsted-Lowry base and Bronsted-Lowry acid. Big picture is Lewis, but specific it's doing what we've just looked at. Down here in the yellow, the partial positiveness of the carbon attracts that hydroxide. So these electrons are going to come in and make a bond between the hydroxide and the carbon, or rather the O and the carbon, and that's going to push this up onto the oxygen, so we wind up with this. Now, because hydroxide was donating its electrons to carbon, which is not a proton, that means that this is a Lewis base and specifically is a nucleophile. It would not be considered a Bronsted-Lowry base. And because this is the acceptor, this would be the Lewis acid, and specifically we'll say it's the electrophile. So let's continue to assess the base. So first of all, just to give you some orientation, we're going to start here and end here, and this is just a progression of a reaction. So A is Lewis acid-base dissociation. So bromine takes the two electrons, off it goes, and we're left with this carbocation. Okay. And then this is where it gets interesting. So B, you have water donating, or oxygen specifically, donating 2 electrons to a bond to form with that carbocation. Because it's not donating to an H, water here is acting as a Lewis base, specifically nucleophile. The carbocation is acting as a Lewis acid, specifically electrophile. And that makes E. Okay, let's go down and look at E. What happens to E? Well, another water comes along and donates its electrons to a proton. Because it donated its electrons to a proton, we're on F, it's a Lewis base, and specifically it's a Bronsted-Lowry base because it dealt with that proton. And because we're also talking about a proton with E, it's that Lewis acid, Bronsted-Lowry acid. So Lewis acid is the big idea. It could be an electrophile or a Bronsted-Lowry acid, but because it dealt with a proton, it's going to be a Bronsted-Lowry acid. And then we've just got the conjugates in G and H. So let's look at complex ions again. Recall that they have a transition metal. So over here you've got cobalt, and then you're surrounded by these ligands. And what's true is the transition metal, like cobalt 3+, it is looking for electrons, so it's an electrophile. And in this case, the ammonia is going to donate those electrons. It is a nucleophile. And we have to have this anion to counterbalance it. Sometimes it's written, sometimes it's not. But most metal ions are found as complex ions. For example, down here we have cobalt and water. And this is a little misleading. It should be OH2, right? Because it's the O that's donating those electrons. This chromium one is pretty interesting because what we have is ethyl-diamine, and we've got 2 lone pair right here, or they did exist there, and that's what's forming these bonds. This is considered a bidentate ligand. And honestly, if you think about it, bi meaning 2, dentate, teeth, right? So kind of clamps in 2 places. So leaving nucleophiles and electrophiles, before we move into some other things, there's just some things you really need to do. And one is you need to memorize your strong acids, because if you know which acids are strong, then you know all other acids are weak. Strong bases, same deal. Group 1 and group 2 hydroxides are strong, except, of course, magnesium, which you may look and see that it has a KSP value, so it goes into equilibrium. So go ahead and memorize these. For your weak acids and bases, what's important to know is they do not completely dissociate in water. They set up equilibriums, and you wind up with a Ka or Kb value. So let's look at this first one. So that's acetic acid, goes into equilibrium. You get H+ ions and acetate ions, okay? And you've got a Ka value associated with it. And you notice reactants are favored in this one because the Ka is so small. Let's look down here at the magnesium hydroxide. Magnesium hydroxide sets up an equilibrium. You wind up with magnesium ions and hydroxide ions. And you've got a Kb value, which tells you that reactants are favored. And ditto up here. Before we move on to pH and pOH, I want to point out a term, amphoteric. Amphoteric substances can act as both an acid and a base. Water is classic amphoteric substance. Another one is aluminum oxide. When you see water, don't automatically say, oh look, acid, or oh look, base. It can be either. So on our way to pH and pOH, we need to look at the autoionization of water. Water ionizes in very, very low quantities to form a hydronium ion and a hydroxide ion. It's very important to note that they are in equal concentrations. So what is true? They are equal. And another way of writing it could be just water ionizing into its parts. You probably guessed this, but in this, reactants are highly favored. So, since this is equilibrium, do you think that temperature affects the position of that equilibrium? And you better say yes. So temperature has an effect on the position of equilibrium. So as we talk about pH and pOH and kW and a bunch of different things, know that what you know to be true, pH of 7 is neutral, that's for 298 Kelvin. That's not for 0 Celsius, that's not for 100 degrees Celsius, it's only for 298 or 25 degrees Celsius. So let's look at pH and pOH at 25 degrees Celsius. A little chart, you've probably seen this a million times. You've got the hydronium and you've got the hydroxide, and you're more acidic if you have more hydronium ions. You're more basic if you have more hydroxide ions. What is always true is that the Kw, so that's the equilibrium constant for water, will equal H plus and OH minus. You can dump a bunch of OH minus into water. It'll shift that equilibrium around. But what's important is the product of the H pluses that remained after the equilibrium shifts around, and the OH minus will be equal to 1 times 10 to the negative 14 at 298 Kelvin. So let's just recap. So we've got water, and it is becoming H pluses and OH minuses. If you add a whole lot, this is a whole lot of OH minuses into water, it's going to shift that equilibrium this way, but all of the H pluses are not going to be removed. So you still have an H plus concentration. And what will always be true, like we said a moment ago, is that Kw will always equal H plus concentration times OH minus concentration. Anything above neutral or below neutral occurs because you've added acid or base to the solution. The other one, if you add acid, the hydroxide, if you add base, the hydronium, works within that equilibrium to make sure that the product is equal to the Kw, which at 293 is 1 times 10 to the negative 14. You are neutral when your H pluses equal your OH minuses. You are acidic when your H pluses are greater than your OH minuses. And you are alkaline or basic if your OH minuses are greater than your H pluses. And this is a word, IB word, ionic product. So the ionic product of water at 298 Kelvin is 1 times 10 to the negative 14. The product of the H plus concentration and the OH minus concentration will always be the ionic product. This is very, very important. This is the whole backbone of how pH, pOH, Kw, all of this works. So on to the main event. I want to remind you that P means negative log base 10. That's just its definition. And if I take the pH, I'm taking the negative log base 10 of the hydronium or proton concentration. If I look at pOH, you guessed it, it's negative log base 10 of OH minus. Something you're probably not as familiar with is pKw, or coming later pKa, pKb. But the rule is it means negative log base 10, so it's negative log base 10 of the Kw value. Okay, so you've got these kind of equations. We've already established it's an equilibrium. So we have Kw is equal to H plus concentration times the OH minus concentration. And properties of logs, if you take the negative log of both sides of this equation, you wind up with pKw equals pH plus pOH. Recall that if you have a multiplication, when you have inside a log, it winds up being a plus. So let's talk at 298. At 298, we know the Kw is equal to 1 times 10 to the negative 14. Therefore, pH plus pOH is equal to 14. And this is what you're probably very, very familiar with. What's very important is that you understand it's at 298 Kelvin. Okay, so let's now do some calculations of pH at 298, so we can use that 14. The first one we'll look at is HCl. You recall that's a strong acid, and a strong acid completely dissociates. That means this concentration represents the H plus concentration. So pH is the negative log of the H plus concentration. pH is the negative log of 0.001. pH is equal to 3. And remember, pH is unitless. So pH is 3. What's important here is double check and make sure it's acidic. Let's skip over here and do the base. So NaOH is a strong base, so it completely dissociates. You get all hydroxide ions, so that is the concentration of your hydroxide ions. So we can't go straight to pH because it's a hydroxide. We have a couple options. We could use Kw is equal to H pluses times OH minuses. Because we've got the OH minuses, we know Kw, we can find H plus, and then we can find the pH. Or we could find POH and then find pH. This is the most common. This is what students pick the most, so let's go with that. So POH, and it is important that you write this out so that you remember you're actually solving for POH. So POH is the negative log of 0.025. POH is equal to 1.60. And you will recall that 14 is equal to pH plus POH. So 14 minus 1.60 is equal to pH. So 12.40 is equal to your pH. That's a basic pH, and that makes sense since this is a strong base. Please pay attention to this, and it's very, very important that if you use this POH, you don't stop. Be aware there is an H plus concentration. It is very, very small. It's apparently 10 to the negative 12.4, but it is present because of that water autoionization. So let's go the other way, and let's do what's the concentration if the pH is 3.24. pH is equal to the negative log of the H plus concentration. 3.24 is equal to the negative log of the H plus concentration. Negative 3.24, very important, is equal to the log of the H plus concentration. You do the inverse log on both sides, and you wind up with 10 to the negative 3.424 is equal to the H plus concentration. And when you put that in your calculator, because you cannot leave it like that, you wind up with 5.75 times 10 to the negative 4 moles per cubic decimeter. Checking out this concentration, does this concentration make sense for a strong acid? And it does. Remember, if the 10 to the negative 7 is that midway point and we're under it and acids are on the lower end, then yes, this makes sense. So let's go to the next one. What's the concentration of lithium hydroxide, which is a strong base? pH of 8.23. We have two ways of doing this. We can get the H plus concentration and then use Kw and then get the OH minus concentration, or we could get POH and then do the same thing we did here. I'm going to go the first route, even though that's the least preferred by students, just to kind of get you familiar with that. If I do the same situation as I do over here, I'm going to find the H plus concentration. So the H plus concentration is equal to 10 to the negative 8.23, which is 5.89 times 10 to the negative 9. So that's the concentration of H pluses present when lithium hydroxide is in water, whatever amount it is. So Kw is equal to the H pluses, OH minuses, 1 times 10 to the negative 14 is equal to 5.89 times 10 to the negative 9, OH minus. So the concentration of OH minus is 1.70 times 10 to the negative 6 moles per cubic decimeter, and that's the hydroxide concentration. And because it's a strong base, meaning it completely dissociated, the OH minus concentration is equal to the lithium hydroxide concentration, so this is actually the answer. What I'd like for you to do now is practice in your book.